I'm about to show you why the claim that this integral has no solution may not be entirely true. This might upset some of you, and I'm sure I'll see comments below, but for those of you who are number ninjas, who've subscribed to my channel and smashed that like button, be sure to stick around because you're in for a real treat. Let's say you tried finding an elementary function that is a solution to this problem. We've learned in math class that there isn't one, and that's true. Because if you use something like integration by parts, you're going to get stuck here. Because when you say u equals x squared and take the derivative of both sides, when you have 2x dx on the right, well, there isn't a 2x in the original problem. And if there was, we could actually solve it that way. And similarly, if you instead try using a u substitution, or y, which I'm going to call it in this case, and with this method, you do it the incorrect way, where you're just simply saying, why can't I set the numerator to some variable y, integrate e to the y, and then plug it back in for x at the end? Try it for yourself. Take the derivative of that answer. You're not going to get the original problem we started with. Okay then, so let's go back to the point of this video. What do we even mean by a solution to this integral? Well, we've learned in math class that theoretically speaking, there is no elementary function that solves this, and that's true. But maybe we should look at the solution of this problem as not so black and white. See, a lot of you are going to be going into engineering and other special fields where you want real world applications to know, hey, when would I use this math in real life? So why don't we look at a different approach to this and use numerical methods to get a really good approximation of the integral, which is basically an area under the curve of e to the x squared. Now, if you remember, there are several methods out there like Simpson's rule, Kata method. I'm going to use the Taylor series method here. And I have another video you can watch. But essentially with this, right, we can take any function and represent it as an infinite sum of terms where you're taking the nth derivative. And if you don't remember this formula, that's okay. But okay, well, in the real world, you're not going to be dealing with infinite series necessarily, right? But the cool thing here is that we can take enough terms out of this and stop at some value of n to get a really good approximation of an area under the curve. What method would you use? Let us know below, because there are other methods that can approximate here in different ways, and maybe you can improve on what I even came up with. Okay, so what I'm going to do is I'm going to center my Taylor series at a equals 0, and I'm going to make the series for the function e to the y. I'm not going to go back to e to the x squared, because e to the y is simpler to work with here, and you're going to see how much useful it is to actually use a simpler form of the problem. So for the n equals 0 to infinity of the nth derivative centered at a of f of x, or f of y in our case, over n factorial times y minus a, which is what we're centered at, all raised to the n, we're saying that a equals 0 and that our function is e to the y. That binomial expansion term on the right, y minus a raised to the n, can be simplified to simply y to the n because a is 0. Okay, now when we actually find what each coefficient term is going to be, we would start with the 0th derivative of e to the y, which is going to be the function itself, right? So then because we're centered at a equals 0, we're going to plug in y equals 0. And that'll result in e to the 0th, which is 1. Similarly, now we move on to the next term and we find the first derivative. So n equals 1 in this case. Well, that gives us the same function, which is e to the y. And then again, when you plug in 0 for y, you get 1. Hold on, guys. If we do this for each subsequent term, the second derivative, the third, the fourth, this is some crazy number ninja mastery because they all equal 1. And this is really nice because when we go to the summation formula here for the Taylor series, notice that for the numerator, this nth derivative term where you plug in a equals 0 is always going to be 1. Well, that's kind of nifty because now we're working with something even easier, which is going to be the sum from n equals 0 to infinity of y to the n over n factorial. And when you take a few terms out, you're going to see the pattern, 1 plus y to the first over 1 factorial, which is simply y, plus y squared over 2 factorial, plus y cubed over 3 factorial. You get the idea. But remember, we're dealing with y, but in the original problem, we had this x squared term, so we got to go back. And this is why I actually did the Taylor series for e to the y instead of e to the x squared. The numbers are easier to play with, and there's nothing wrong with now just simply plugging in x squared wherever we see y. So instead of y raised to the n power in this summation formula, we would have x squared raised to the n, in other words, x to the 2n. And this produces a new series where, looking at the series we got above, Anytime you saw a y, you have x squared now. So the denominators are the same, but now you've basically got even powers of x. Okay, going back to the point of this video, we can get a really good approximation now, and there's a real cool real-world application of this. Say you're in a cool startup company and your boss is thinking about giving you a promotion, and he's giving you some sales data for the year over January through December from this year until next year. So from year 0 to year 1. And he wants you to give a rough estimate of your profit margin, which is the area under the curve. Now, in the real world, we're not necessarily talking about theoretical math, about a true elementary function that's a solution to this problem. But we can use really good numerical approximations here, and I'm going to do that. I'm going to choose 4 terms from the Taylor series approximation of e to the x squared. And notice how this becomes now an approximate integral where we are taking the integral of a sum of polynomials. Remember that with the rules of calculus, this is the same as integrating each of those polynomial terms separately and adding the results. And I'll leave that to you as an exercise, because when you evaluate that then from the limits of integration from 0 to 1, you're going to get a really good approximation to the area under the curve.